All right. Hello, everyone. I apologize that last video ended kind of abruptly. There was someone at the door, and I tried to hit pause and accidentally hit stop, so it just cut off very suddenly. So what I was going to do next, I've got a couple of chemical reactions up here. I want to go through and we'll identify the Bronsted-Lowry acid and Bronsted-Lowry base in these three chemical reactions. Okay? This one is HC2H3O2. You might recognize that as acetic acid, which is kind of a hint, frankly. With hydroxide ions to make water and acetate ions. In this one, we've got fluoride reacting with water to make HF and hydroxide ions. And here we've got HCl plus aqueous ammonia, giving us NH4 and chloride ions. Okay. All right. Take a minute. You can pause the video. Take a minute, go through these, and identify on the left-hand side. Identify the acids and bases in each of those three reactions. Okay. After you've done that, unpause it, and we'll compare our answers. All right. In this first one, I said this was acetic acid, which obviously is kind of a clue, right? And if you just look at the equations, you can see this is, if you look at the formulas, I should say, this is HC2H3O2, and over here, it's C2H3O2. So clearly, it's lost that hydrogen, right? So this hydrogen is being removed, and where does it go? It goes over here to the hydroxide in order to make water. So an H plus is being transferred from acetic acid to the hydroxide. That means this is the proton donor, which makes it the acid. This is the proton acceptor, which makes it the base. Okay. All right. In this case, you can find this species on both sides. Here's your fluoride. Here's the fluoride species. Here, the fluoride has a hydrogen with it. Here, there's nothing, right? So clearly a hydrogen has been added to the fluoride. Where did that hydrogen come from? It came from the water molecule, right? Because this water molecule originally is H2O. It's got two hydrogens. And over here, it's only got one hydrogen. So clearly a hydrogen must have been transferred from the water molecule to the fluoride. So that means this is the proton donor, the acid. This is the proton acceptor, the base. And if we look at this one, we've got NH3 over here, NH4 over here. So clearly a hydrogen has been added to the ammonia. And that hydrogen came here from the HCl, leaving it with just chloride. If I give you a problem like this on the test, you don't have to do this little arrow thing. I'm just doing that to help make it more clear. So this is the proton donor, this is the acid, and this is the base. Okay. All right, so if you did this on a quiz, you can draw that in if you want. I definitely wouldn't take off of that. You can do that. But that's all I would expect you to do. Okay? That's how I would expect you to answer this kind of problem. All right. Let me make another point here. All right. So in this reaction, the water has transferred a hydrogen ion from the water to the fluoride to give HF and OH minus. Okay. The water is the acid, the fluoride is the base. But once you add a hydrogen to the fluoride to make HF, now this fluoride has a hydrogen on it that it didn't have before, right? So the hydrogen was added. The hydrogen could then be given away to someone else, right? So now that this has a hydrogen added to it, it now has a hydrogen that it's capable of donating to someone else or giving away. Right? So that means this species is capable of donating a proton. So this species is has the potential to act as an acid. Okay. And so whenever you have a pair of species like this, you take something, you have a base, you add a proton to it, to add one hydrogen to the formula. We call this the conjugate acid. So we would say hydrogen fluoride is the conjugate acid of fluoride. In the same way, here, the water molecule gave away a hydrogen, so it was acting as an acid, right? But from the spot where it gave away that hydrogen, it now has an empty spot where it could accept a hydrogen, right? So this now has the potential to act as a base. And so we would say that let me write that word out. All right. So we would say that hydroxide is the conjugate base of water, right? Anytime you take something that's an acid, it's capable of donating a proton. Once it loses the proton, it has a spot where it could potentially accept one, so it becomes a base, and we call that the conjugate base. Okay. All right. Let's look at a couple of these. All right. Let's see. I'm going to give you a list of acids. Actually, I'm going to write this differently. Same compound, but I'm going to write the equation different. Write the formula differently. All right, so we've got HCl, C2H3O2, NH4 plus, H2SO4, that's sulfuric acid, HSO4 minus, that's the hydrogen sulfate ion, and water, okay? And what I want you to do for each of these is to determine what the conjugate base is for each of these acids. Each one of these is an acid. I want to know what the conjugate base is, okay? And let me tell you how to do that. When this acts as an acid, it's going to lose a hydrogen ion, right? So you just need to take this species, remove the hydrogen, okay? And because the hydrogen ion has a +1 charge, you have to change the charge here, okay? So when HCl loses a hydrogen plus ion, it's going to leave a chloride anion. So the conjugate base of hydrochloric acid is chloride. Okay. Same way, this is acetic acid. We're going to remove one of the hydrogens. That gives us the acetate ion. And because hydrogen has a +1 charge, if we take away a +1, the part that's left over is going to be -1. All right. Go ahead and hit pause and write the formula for the conjugate bases of ammonium ion, sulfuric acid, hydrogen sulfate, and water. Okay, now for ammonia, on ammonia, just because of the electron affinities, the way this formula is written, the hydrogens are on the right instead of the hydrogen all the way over on the left, as it typically is. But still, if this is acting as an acid, it's going to lose one of its hydrogen ions. So it's going to go from NH4 to NH3. Okay? And because the hydrogen that's lost has a +1 charge, the total charge here has to decrease by 1, basically, right? Since this was already a cation, when we lose an H plus, we're left with NH3, which is neutral. Sulfuric acid, when this loses a proton, here there are 2 protons over here. There are 2 hydrogen ions that could be lost. But when we do this, we're always going to do this one step at a time. So with sulfuric acid, if it loses a proton, loses one of those hydrogens, we're left with HSO4. And again, the charge has to go down by 1 because we've lost a +1 hydrogen. So it goes from neutral to -1. Hydrogen sulfate ion also can act as an acid. When this loses a hydrogen, we're left with sulfate. And here our charge is already negative, right? The charge is -1. If we lose a +1 from that, charge goes down 1 more, and we get -2. And water, if we take a hydrogen ion off of water, we get hydroxide. Okay. All right. So these are the acids, and these are the conjugate bases. Okay. 2 things to point out. One is, see, we've got hydrogen sulfate over here as the conjugate base of sulfuric acid. We've also got hydrogen sulfate here as the conjugate acid of sulfate. Okay. So HSO4 can act as both an acid, as it does here, or as a base, as it does here. So that means, what's the word that we would use to describe HSO4, or HSO4 minus, I should say. Hydrogen sulfate ion is amphoteric. It can act as either an acid or a base. Okay. All right. Now, I guess I'll also mention the term conjugate base. It's kind of, it's a relative term, right? So if we call this the acid, this is its conjugate base. If we call this the acid, this is its conjugate base. But we could have, just depending on how we were focusing on things, we could say chloride is a base, and HCl is its conjugate acid. Right? We could say acetate is a base, acetic acid is its conjugate acid, ammonia is a base, NH4 plus is its conjugate acid. Right? Just depends on which one we're focusing on. I wanted to make the point that an acid and a conjugate acid aren't 2 different things. It just depends on which one you've defined first, right? The partner of that is called the conjugate acid or conjugate base. But that's really just a relative term. Okay. All right, let me do just a couple more. I want to do a couple of these going in the other direction. This is a really common quiz or exam problem. Here's a list of acids, what are the conjugate bases? Or here's a list of bases, what are the conjugate acids? All right, so in this case, to find the conjugate acid of a particular base, we just have to do the opposite of what we did last time. Last time we removed a hydrogen ion. Now we're just going to add a hydrogen ion. So if we've got nitrate and we add a hydrogen ion, we get nitric acid. Okay? And also, same thing with the charge. Since this hydrogen ion has a +1 charge, the net charge as we go from here to here is going to go up by 1 because we're adding an H+. All right? So if we take hydroxide and we add an H+, we've now got two hydrogens. So it goes from OH to H2O, and the charge goes up by 1. This was -1, so now it's 0. For water, if we want to create the conjugate acid of water, we have to add an H plus. So this is one of those examples where it's useful to write this as H3O plus, right? And sulfate, if we want the conjugate acid of sulfate, we just add an H plus, and we don't add two H pluses. With Bronsted-Lowry acids, when we're doing these reactions, we'll always add hydrogen ions one at a time. Right? So even though we know there is sulfuric acid, which is H2O, we're just going to add one. Just going to add one hydrogen to that. Okay? So we add a hydrogen, and the charge goes up by 1, so it goes from negative to negative 1, and we get that hydrogen sulfate ion again. All right? Lovely. Okay, that might be it. Okay, yes, it is. That is it for the first introductory topic in acids and bases, and we'll be back with another lecture. What's our next topic? Oh, I don't have the table of contents with me right here. The next topic will be autoionization of water and the pH scale. So we will do that next time. All right. Until then, I'll see you later.